Well, this is our electric circuits course offered in second semester spring 2020 to the students of electrical engineering at UT Lahore, and I'm Dr. Khalid Emerson. This is our textbook. I'm using its 8th edition. If you have prior editions, it will be okay. In today's discussion, we'll discuss interface circuit design. This is the textbook reference, and this is part 1 of my lecture on the interface circuit design. Now, what is interface? If you look at the left hand side, this is the source, and the box over here, it shows the source. And in the following examples, we'll be only using the Thevenin equivalent of the source circuit with the Thevenin voltage and Thevenin resistance and Thevenin voltage. The whole circuit will not be shown. Similarly, at the load side, we'll be using single resistance RL, but this load may consist of several resistors. It may be just another circuit, and in a typical amplifier speaker example, this load may be a speaker, source is the amplifier, load is the speaker. Now, why we need this interface circuit? We use this interface circuit. We use this interface circuit over here, this interface circuit, to connect a source to a load. There are many ways in we can use to connect source and load, and in this discussion, in today's lecture, we'll discuss few basic types of interface circuits. There is a wide variety of interface circuits. We'll be using interface circuits with only resistors. We'll be using only resistors in the interface circuit design. So, very simple types of interface according to the domain of our course are basically 4. So, first of all, there are a few more words about an interface. Usually, this interface circuit, we show the input voltage and input current, and output voltage and output current, V1 I1, V2 I2. In some text, you will also see this direction, the red one, this direction of the output current. So, whatever current direction or whatever voltage polarity we use will be just as a reference. It will be as a reference, and we will, in the design and our analysis, we will only be using these references. Now, in this interface circuit, we have an input port consisting of two terminals or a pair of terminals, and a pair of terminal at the output, and this will be called output port. Due to input port and output port, it is also known as two-port interface. And in some texts, you will also see two-port networks, analysis of two-port networks, which is very important topic in electrical engineering, and you will study many types of interface circuits in the following courses. But due to the scope of our course, this course circuit analysis is offered in second semester to the students of electrical engineering. We will discuss only few basic types of interface circuits. So type number 1, it is known as simple pass-through interface, and it is often omitted or not shown because in this interface shown here, in this interface inside the box over here, you will see no component, no element in it. Simply the input is connected to the output. That is why it is known as pass-through, and it is not even shown. On this side, at the left hand side, we have input, and at the right hand side we have output. This is the input or source circuit, and at the output we have a load. Now, in this very simple and basic type of interface known as pass-through, we have a source circuit over here at the left hand side, and this source may be fixed or adjustable. This is very important. It may be fixed or adjustable. We will discuss an example where the source is fixed. Looking at the output, the load is however adjustable. So with this adjustable load, what we will be doing, we will try to ensure a specific voltage at the output and specific current. Note that this voltage polarity and direction of the current, it is all relative. We have to stick with this voltage polarity and current during our analysis. So this is a very basic type. Basically in the interface there is nothing. We connect the input to the output directly, while the output is adjustable. So with the adjustable output, we can meet the output load conditions on the output load, or a specific output load voltage and specific output current, because the load is adjustable. So the second example is a series resistor. You see, this is the input port. At the input port we have two terminals, at the output port we have two terminals. At the input port, source circuit is not shown, and at the output load is not shown, only the interface is shown. Only the interface is shown, and in this interface we have only a resistor which is in series. That is why it is known as series resistor. So in this type of interface, our source is fixed and load is fixed. What do we do here? We design the interface, means we want to find a value of resistor such that the power is delivered from a fixed source to the fixed load in order to meet specific current, voltage and power conditions. So what will be given? It will be the output voltage. We want to maintain this output voltage, and we want to maintain this output current. And you know, power is product of voltage and current, and definitely we can compute the power. We will also be discussing power dissipated in this interface. Power dissipated in this interface. Our next type is a parallel resistance. So in here, in the interface, we have a parallel resistance over here, and while this is our input port, and the source circuit is not shown, and this is the output port, and the load at the output is not shown. Again, we would like to maintain some voltage and some current over here. To maintain a specific voltage and current to deliver a particular current, voltage and power to the load from a fixed source. Note that load is fixed and source and load both are fixed, and we will only be changing this resistance over here in this interface. Now, our next interface type is known as L-pad left and L-pad right. We call it L-pad left when we have a resistance at the input side, and we call the other one L-pad right because there is a resistance at the output side. We'll be using labels in the following examples R1 and R2, and here R1 and R2. Again, we would like to maintain specific voltage and current at the output side and sometimes at the input side as well. So let us call it V2 and I2, and over here this is I1 and V1. V1, I1 at the input side, V2, I2 at the output side. So similarly over here, the current I1 and the voltage V1 at the input side, current I2 and voltage V2 at the output side. What is the purpose of this interface? To deliver a particular current, voltage or power to the load. Note that our source is fixed and load is fixed. And in this design, we will sometimes we will see that L-pad left meets the requirements of current, voltage and power to the load, as well as L-pad right. Both may fulfill the specific conditions. Then we will select best out of these two due to power consumption in both of these. Other types of interface circuits, there are many types of interface circuits we can use, and few types I can mention over here. It is a T-type interface, and I will show it over here. T-type interface is like this, and this is due to the letter T. So this is the input side and this is the output side, or input port and output port. Pi, due to its name, so its shape is like pi. So again the input and output. And pi. And there is O or O-pad, also known as O-pad. O-pad is like we have a resistor here, resistor here, resistor here, and resistor here, and due to its shape it is known as O-pad over here. And there is a wide variety of possible interface circuits to meet the specific or given conditions of the input and output voltage and current and power. Now in our examples, in these examples, we will be using only resistors. You can see over here in it we use only resistors. In series we use only resistors. In parallel resistor, and in series resistor only resistors over here. Now one thing I forgot to mention, this series interface, it suits best when the source it consists of a voltage source, and the parallel, it suits best when the source circuit, it is when we have a current source. And now other interface types. In other interface types, we can use, other than resistors, we can use transistors, operational amplifiers. We'll be discussing in chapter 4, capacitors, inductors, and even transformers can be used in interface circuits. And what is our requirement? Why we design these interface circuits? To meet the given or desired conditions on the input voltage, on the input current, on the output voltage, and on the output current. So now I will present few examples of each type of interface circuit design. In this example, the source circuit shown here, again it consists of its Thevenin equivalent. Actual circuit is not shown. This is the Thevenin equivalent of the source, and a single resistor is connected at the load side. Now we assume that we can vary the load. RL is adjustable. When load is adjustable, the case is very simple, and we see that if I redraw the source circuit over here, so this is 10 volts, this is 100 ohm, and this is a pair of terminals A, B, and this pair of terminals C, D. Now A, B, we would like to see what is the maximum voltage over here, V maximum. So V maximum is when output is open circuit over here, and therefore V maximum across AB is equal to 10 volts. And then we see what is the maximum current. So before, here we have shown that what is the maximum voltage the source circuit can provide. Now here we see what is the maximum current the source circuit can provide. For maximum current, we see I short circuit, and I short circuit is the maximum current. You should know, due to Thevenin equivalent, Norton equivalent, I short circuit is the maximum current. So maximum current is 10 over 100. This is 1 over 10, and the source circuit can provide maximum voltage of 10 volt and maximum current of 100 milliampere. Because the load is adjustable, we are free to choose any appropriate value of the load voltage, of the load resistance, to meet these two given conditions. So the two conditions are on the current which is flowing through the load and the voltage which appears across the load, across CD terminals. So this is the voltage and this is the current in the original circuit. As we can adjust the load, we will see that a simple pass-through interface where we connect the source to the load side directly without any element in it. In this case, we see that, look at the circuit diagram. I will delete this now, and there is no interface over here. The current which flows through this mesh is the same current which flows through the load. Now with this, we will see what is the voltage which appears across the load, the voltage over here. The voltage is across RL, because it is a simple mesh with the two resistors, therefore it is a voltage division, and this is the voltage which appears across the load. And this voltage, due to the given output voltage or voltage across the load condition, this voltage should be equal to or greater than 4. If we proceed further, we will find that RL is equal to 66.7 ohm. I'm saying that if we solve this equation over here. Now we see what is the current. Due to the current condition, the current I in this mesh, the voltage is 10, one voltage source, and two resistors, it is 100 plus RL, and due to the current condition, this should be greater than or equal to 30 milliampere, means 0.03 ampere. And now if we solve this equation over here, this is RL. From here we get 233.3 ohm. It shows that any value of RL between 66.7 ohm and 233 ohm will meet these two conditions, the current and the voltage condition. I have done some calculations over here. I'll take it to the circuits above so that you can see both over here. Now, as the load resistance can be between 66.7 and 233.3 ohm, we have many choices of the resistance. So initially say RL is 100 ohm. If RL is 100 ohm, we will see that the output voltage is 5 volt. And our voltage condition, output voltage condition over here is that the output voltage should be greater than 4. Then we see what is the current in case of 100 ohm resistance, and the current is 50 milliampere. Now see the condition on the current, it should be greater than 30 milliampere, so it meets both the requirements. Now then we select RL of 150 ohm. With 150 ohm load resistance, output voltage is 6 volt and the current is 40 milliampere. Again, this resistance can meet the given requirements. And then say we choose another value, 200 ohm. Due to 200 ohm load resistance, the voltage at the output is 6.6 and the current which is flowing through the load is 33.3 milliampere. Therefore, we can say that this load resistance meets the condition, this load resistance meets the condition, and this load resistance also meets the condition. So because it was a very simple case, so we can design the interface, which is basically a pass-through. And what we have done, we have proved that a simple pass-through interface circuit will be sufficient enough. Note that Why it is sufficient? Because it is in this case we are able to we have a choice of adjusting the load resistance. In the textbook you will see an example, and to save time I will omit this example because it is straightforward and you can understand it quite easily. And now I select another example from the textbook, and this is this example. Again, in this example the source circuit is shown here. Only the Thevenin equivalent of the source circuit is shown, which is 15 volt and 50 ohm resistance, Thevenin equivalent. And load is a single resistance. And now in this example, this RL is fixed 200 ohm, and you also see that the source circuit is also, source is fixed and load is fixed. Now we see what should be the interface over here. What should be the interface over here? First of all, we will check that if the pass-through interface will be enough, if the pass-through will be enough for this. So let us check that. So before checking, we should know the conditions we should meet. In this circuit, what is required is that V2 is equal to 5 volt. This is the only requirement in this case, in this example. So let us see if we can use a pass-through interface. And again, I'm repeating again and again so that you can remember quite easily. So pass-through means no interface. So if we connect it directly, what is the voltage? What is the voltage over here? The voltage over here is 200 divided by 200. Again, it is a simple mesh, a single mesh, multiplied by 15 volt, and this is 12 volt. 12 volt is the output, and this 12 volt output, if you see, so it does not meet the condition. So simple pass-through interface is will not work. Now again, the original circuit, and now we think of another choice. Of interface circuit. So as the output over here, this output, due to the required condition, is 5 volt. We know that, we know the voltage across the load resistance, and we know the value of the this load resistance. Therefore the current is 1 by 40 ampere, or this is 25 milliamperes. And now we think of an interface, and this interface, let us try a series resistance. In this interface, we will find the value of R which can meet the required condition, which is at the output voltage, which should be 5 volts. Now, we see a single mesh over here, and in this single mesh the same current is flowing through 50 ohm resistance and the interface resistance and through the load as well. We write a mesh equation over here. So in this mesh equation we start from 50. So this is 50 I current is flowing, plus R multiplied by I is the voltage across this resistance, and then we have this voltage, the 5 volt. This is given. We have to meet this requirement 5, and then equal to, closing the loop over here. So this is voltage rise. Now we know that in it I is equal to, due to the, look at the circuit diagram, due to 200 ohm resistance and due to this condition, the I is equal to current flowing through the load is 140 ampere, or this is equal to 200 milliampere. Due to this given condition, we see that R, this equation number 1, this R is 350 ohm. If we select 350 ohm resistance, it will meet the condition. We can also, with this R equal to 350, we can verify that the output voltage is 5 volts. Again, I repeat the circuit over here in order to see another possibility of the interface and resistance. It is same resistance, RL is equal to 200 ohm, and the interface over here. So now we think of a parallel resistance over here, and we find what should be this R to meet the required condition. Again, note that the required condition, we have only one required condition, only one condition. To meet one condition, usually we need one variable, and either it is a series resistance interface or a parallel interface with parallel resistance. Now look at the circuit diagram. So this condition, which is required, the 5 volt should appear across RL, and this current is 25 milliampere. 5 volt across 200 ohm means 25 milliampere current is flowing. Interestingly, we see that the RL and this R of the interface, they are in parallel. Therefore, the same voltage appears across both of these resistors. Now we see what is this current. Say it is I1. What is this current? Say this is I2, and this current over here, say this is I3. We know what is I3 due to the given load voltage condition and the given load resistance. Again, I repeat, this is 25 milliampere. Now, what is I2 which is flowing through this R? Look at the circuit diagram which is flowing through this R. This is 5 volt appears across it, and the resistance is R, and this R is not known yet. So what is I1? I1, look at the circuit diagram. What is I1? If we see the loop, over here, in this loop, this I1 is 15 minus 5, because we know the voltage over here, 15 minus 5. So this is voltage rise and this is voltage drop. So the net voltage across this 50 ohm resistance is 15 minus 5 and divide by 50, and this is equal to 0.2 ampere or 200 milliampere. Now just over here to make it clear, okay, and now we see this node. We apply Kirchhoff current law at this node, and this is I1 is current flowing towards the node, I2 is leaving, and I3 is also leaving. So what is I1? I1 is 0.2. What is I2? I2 is 5 divided by R. And what is I3? I3 is 25 milliampere, 0.025, which gives a value of resistance R of the interface, and this is 28.57 ohm. So this value of resistance in the interface will meet the required condition. Now the question is that we have the interface. I will show you the interface only. We have this interface series, and we have a parallel interface with parallel resistance over here. And which one is better? One way to choose the best out of it is out of the two is to see the power consumption. And over here, just to repeat the circuit, and this is 15 volts and 50 ohm and a series resistance, and then this is RL, and 5 volt appears across this, and the resistance which we calculated before is 350. This resistance in the interface 350 ohm. This is also 50 ohm and 200 ohm. Now you see what is the current. Current flowing through this mesh, this current, we know this current 0.025 ampere, because we have 5 volt across the load of 200 ohm, and we have done it before. Look at here, 350 ohm resistance, and then we see what is the voltage here. What is the voltage here? We know the voltage here. So the voltage across 50 ohm resistance, if you calculate, I will again recheck it. So this is 0.025 milliampere multiplied by 50 ohm, and this is 1.25 50 multiplied 0.025, this is 1.25 volt. So 1.25 volt. Similarly, if you see the voltage over here, voltage across 350 ohm resistance, so it is the current multiplied by 350, this is 8.75. Now move around this mesh. We have a 15 volt rise if we start from here, and then the drop across 50 ohm resistance 1.25, the voltage drop across 350 ohm 8.75, the voltage drop across the load of 200 ohm resistance is 5, and if you add these two, it should be equal to 15 volt. So now calculate power consumption. Now the power consumption across 50 ohm resistance, this power consumption, power is the product of V and I. R, it is V square over R it is I square multiplied by R. We can use any expression. The power which I have calculated before, 0.3125 watt. The power consumption in 350 ohm resistance of the interface, 0.21875 watt. The power consumption in the load resistance, this is 0.125 watt, and if we add all these, so the total power consumption is 0.374 watt. And now we see the parallel interface. This is 50 ohm resistance, and this is 15 volt, and the interface, and then the output. At the output we have load resistance. So what is our interface? The interface is the parallel resistance, and see what was the parallel resistance in this case. It was this one, 28.75. So over here this is 28.75. Note that the output voltage is 5 volt, and this current which we have used before, this is 25 milliampere. The voltage across this resistance is also, interface is also 5 volt. So in this case, we know that this is voltage rise, and this is voltage drop, and this is also voltage drop. Therefore, we can over here quickly say that this voltage is 10 volt. So again verify, move around this mesh. 15 volt is rise, and then this is 10 volt drop, and then 5 volt drop, and loop is complete. Here we know the voltages, and we will compute the power, and this is V square over R. Note that we can also compute the power using I square R. So what is the power consumption in 50 ohm resistance? This is 2 watt, and this is then what is the power consumption across 350 ohm resistance of the interface? This is 0.875 0.877 7 watt. And what is the power consumption across 200 ohm load resistance? 0.125, and what is the total power consumption? This is 3.002 watt or 3 watt. Now note that over here we have done the analysis based on uh, the power consumed in each element. Just look at the interface. So in series interface, power consumption in the interface circuit element, which is only one resistance, is 0.21875 watt, and over here in the sorry, it is I should have written over here. I will. This is 28.75 ohm resistance. So I think you will tolerate it. This I mean. So the power consumption, you can see there is over here. So based on this power consumption, we will select this because it is much less than the power consumed over here. Another thing, the total power consumed 0.374, and over here is 3 watt. So we select this series interface type, and we reject the parallel interface due to power consumed in it. Now I will discuss another example in it, another example in the interface circuit design.